All right, let's get right into it. The Amazon rainforest, it's just colossal. It's vital to the planet, and as we all know, it's under threat. But think about this. How do you actually keep an eye on something that massive? How do you really know what's happening there? Well, today we're going to explain the incredible science of how we track the Amazon right from orbit.
It kind of sounds like a riddle, doesn't it? But how do you count a forest is honestly one of the most important questions in all of climate science. Obviously, you can't count the individual trees, so you have to count the area of the forest. And let me tell you, getting that number right is incredibly hard, but also absolutely fundamentally critical. And here's exactly why it's so critical. Right now, best estimates tell us that tropical deforestation is responsible for somewhere between 7 and 14% of all annual CO2 emissions from human activity. That is a huge chunk. It puts tracking forests right on the front lines in the fight against climate change. So, we all know deforestation is a massive problem. What's stopping us from just fixing it? Well, it turns out the solution is tied directly to how well we can measure the problem, and that has created this massive financial and political challenge. You see, a key part of the global strategy is a program you might have heard of called REDD+. And the idea is pretty simple, actually. The international community offers financial incentives, we're talking real money, to countries that can actually prove they are slowing down the rate of deforestation.
And that right there is the heart of the problem. For a program like REDD Plus to even work, you need data, and not just any data. You need credible, unbiased, frequent reports on exactly how much forest is being lost or maybe even gained. Without that rock-solid, trustworthy data, the whole system of financial incentives it falls apart.
For decades, this whole measurement problem was a giant roadblock. But then, a revolution in remote sensing gave scientists a brand new, incredibly powerful toolkit. Essentially, a new eye in the sky, one that could watch the entire planet.
The real game changer came in 2008. That's when the entire archive of Landsat satellite imagery was made totally free to the public. I mean, this unlocked decades of historical data. And then with new satellites like Landsat 8 and Sentinel-2 coming online, it just kicked off a total golden age of Earth observation. So now you have all this data pouring in. Scientists had to develop powerful new tools to make sense of it all. And one of the most important is an algorithm called CCDC. Its job is to look at the entire history of satellite images for every single 30 by 30 meter patch of land on Earth.
So how does this thing actually work? Well, you can break it down into a 4-step process. First, for every single pixel, the algorithm builds a model of what its normal ups and downs should look like through the seasons. Then it monitors every new satellite image that comes in and compares it to that model. Third, if the new pictures consistently look different from the prediction, it detects a break. That means a real change happened on the ground. And finally, it classifies what the land was before and after that change happened.
And this lets us see the actual life story of one tiny patch of the forest. It's amazing. Take this one pixel in the Colombian Amazon. The algorithm saw it was primary forest for years and years. Then, bam, in 2005, a break. It was cleared for pasture. A few years later, it started to grow back into what we call secondary forest. But then in 2011, another break. It was cleared again. This level of detail, for the entire planet, it's a total game changer.
And this is a big but, even with this incredible technology, the maps it creates aren't perfect. A map is just a model of reality, right? To get to the real legally defensible numbers that you need for these big international climate agreements, scientists have to use some really clever statistics to find the truth that's kind of hidden between the pixels. So one of the biggest problems they run into is something called an omission error. And it's pretty much what it sounds like. It's an error where the map omits a change that really happened. The map might say stable forest, but in reality, a section of trees was actually cut down.
The best way to think about it is like a security camera that just glitched for a second. The final footage shows nothing happened, but an event was definitely missed. Now, imagine that happening in a forest that's bigger than most countries. Even a tiny rate of these missed events can throw your final numbers off by a huge, huge amount.
So how in the world do you find these missing events? Well, researchers came up with a really elegant solution. Instead of searching the entire, vast, stable forest for mistakes, they created something called a buffer stratum. It's basically a search zone drawn around all the deforestation they had already detected. Why? Because change is much more likely to happen right next to other change.
And get this, the result of this simple statistical trick was just incredible. By focusing their search for errors inside this smart buffer zone, they slashed the uncertainty in their final deforestation estimates by up to 98%. It just made their final numbers dramatically more precise and a whole lot more trustworthy.
Okay, so now we have this powerful satellite algorithm, and we have this clever statistical fix to make it even better. So let's take a look at what this powerful combo actually revealed about what's happening on the ground in the Colombian Amazon.
What the study found was that between 2013 and 2015, about 103,000 hectares of primary forest were lost, mostly turned into pasture for cattle. Now, during that exact same period, only about 29,000 hectares of that pasture even began the long process of regenerating back into secondary forest.
The study puts it really bluntly, quoting here, less than the equivalent of 30% of the post-deforestation landscapes was estimated to have begun to regenerate. So let that sink in. It is not a one-for-one exchange. For every 10 acres of pristine primary forest that gets cleared, less than 3 of those acres even start the long journey of recovery. The rest just stays pasture or becomes something else entirely.
And all of that brings us to the final and I think the most important point. Why go through all this trouble? Why all this complex math and statistics just for a few percentage points of certainty? Why does this level of scientific precision matter so much? Well, the answer becomes crystal clear when you just look at the data. A simpler, less rigorous method gives you huge uncertainty. You can see that represented by those big error bars. But the advanced method from this study, it collapses that uncertainty, producing this tiny, reliable range. You go from having a vague guess to having a number you can actually build policy on.
Because at the end of the day, it all comes down to one word: trust. For countries to cooperate, for those billion-dollar financial agreements to work, for all of us to really know if we're winning or losing the fight, we need numbers that we can all believe in. This science is what builds that foundation of trust.
Which really leaves us with a final question to chew on.
This explainer shows that just seeing the forest from space is the first step. But it's our ability to measure it with this incredible precision and confidence that truly gives us the power to protect it.